Okay, thermodynamics 1. I never seen this many students. Wait a minute.
I hope so. I think he's correct. So that'd probably be it. I hope. So that's. Well, that's, you know, that's probably bad. Spring 47. I'll get that's the whole. Used to sit.
Okay, so this is thermodynamics 1. My office hour is right after this class, 10:45 to 11:30. In my office, ET 238 and 234. Or you can also see me via WebEx. The link is available on Blackboard. Excuse me, you know, I have a chapter brief right now for bleeding. Never happened before. Okay, so the textbook is this one, Fundamentals of Engineering Thermodynamics, 9th edition. And you may receive an email from the bookstore that you have an access on Blackboard, right? If you don't like that, you don't have to, you know, to use it. You can just get a reprint and get a hard copy. That's fine by me. I just, you know, use that, you know, the online version because I heard that it is cheaper. But if you find elsewhere, maybe Amazon or somewhere else that has a lower price textbook, you can buy that one instead. Okay. I think you have about 2 weeks to get a refund if you want to prefer, you know, the using the one from Amazon. That's very fun. Yeah, it was cold yesterday. I think, you know, there was a heater running in my room, in my bedroom. I have a dry mouth or something. Anyway. Oh, by the way, if you want to, if you have an older version, that's fine by me. But you need to find a friend who is rich enough to buy the latest version because the homework assignments are based on the latest version. You know that publishers keep changing the order of the problems, changing color from red to blue and trying to sell more books, not representing them. So if you have a older version, fine by me. Okay. There will be 3 exams, 2 midterm exams, and 1 final exam. The date of the exam will be discussed at least, you know, the 1 or 2 weeks in the classroom. So it depends on, you know, how much we progress. Usually, this class is going to cover 8 chapters from 1 to 6 and 8 and 9. So the first exam is going to cover from chapter 1, 2, and a half of chapter 3. And once we complete the half of the chapter 3, then we can determine, the when we are going to have our first exam. The date of the exam is going to be at least a week after we complete, the materials that is going to be covered by the exam. Okay, so we have plenty of time. The second exam is going to be not comprehensive. It's going to be from, the where we ended for the first exam until chapter 5, and then the final exam is not comprehensive again. It's going to be from chapter 6, 8, and 9. Okay, so each is going to be 30%. And the homework assignments, we are going to have one homework assignment per chapter. So you will see 8 homework assignments. That's going to be 7%. And by the way, there is no, there is no rule that you need to have these many homework assignments before a specific exam. And the exam and homework assignments, they are two separate, the tools to evaluate your progress. So don't complain that there's a homework number 3, which should cover chapter 3, but that due date is after or before the first exam. There is no, the relation between homework assignments and exams. Okay. And attendance, I'm going to check attendance maybe 1 or 2 times. So please make sure that you will be here on the day. If you miss that, you will lose 3 points. Then when we are going to check attendance, when we have the lowest attendance, that's the judgment day, we're going to check the attendance. So that is going to be free bonus 3%. Okay. The final grades will be based on the following grade table: 94% above, A and A minus, B plus, etc., right? Late assignments will be reduced by 20%. So if you miss the deadline for the first exam, that's okay. You can submit on a later day, but be sure that there will be 20% penalty. Okay? And there's no late work is accepted after the final exam. Those I don't want to work during the winter break. Okay? By the way, the homework assignments are going to be submitted to the Blackboard. Okay? So don't submit a hard copy. Because I don't want to see students complain that I submitted and then you forgot away. It's not going to happen. Okay? So you can write on a piece of paper, or you can also, solve, the problems on your Word file or text file or anywhere, or on a Paint or Photoshop, doesn't matter. Convert it to a PDF and upload on Blackboard. There will be, the multiple submissions are allowed. So if you made a mistake during your submission, you can resubmit, but only the final version is going to be graded. So if you accidentally submit after the due date, there will be 20% penalty. So be careful, okay? If you do not know how to, convert your, let's say, JPG file or, the Word file into a PDF, you can go to ilovepdf.com or use any of the computers in the university, and you can log into Acrobat Pro. You have a subscription, pay a lot of money for that, and then convert it to PDF. Don't submit a PDF. The size is about 1 gigabyte. That takes about 20 minutes for me to download. Okay, so you can optimize the size of you can compress PDF file. You know how to do that, right? Do that and then submit. As a single PDF file, don't submit 20 different PDF files. I have to download all one by one. not me, maybe teaching assistant, but please make a very compressed single PDF file, okay? And make sure that you show your solution so we can understand, how you, solve the problem, not just, the final answer, okay? The same rule goes to your exam. You need to show how you solve the problems. So in that case, if you miss, if your final answer is not correct, so I can evaluate, based on your solution, okay? Any question? No? Oh, no more bleeding. That's interesting. I'm very good at hearing. Like, what is that? There was a X-Men. No, who is the guy who can hear very fast? Logan, right? No, you don't know that? Wolverine. Yeah. Wolverine. Yeah, Wolverine. Isn't it Logan his name? No, right? Yeah. By the way, I made a very nice lecture PDFs and upload it on Blackboard. Please download them and then use them, okay? You don't want to read this entire textbook from pages 1 to how many pages? 600 pages. And in this tiny, tiny font, you don't want to read all of them, right? So use your lecture notes as a primary materials to study. And if you have a question, then you can go to this textbook and find the section to learn more, okay? By the way, it is very interesting, that every university in this country is complaining about, the decrease of enrollment. And surprisingly, look at this class. I hate this class. It's hard. You know that in this building, the other half has a very good air conditioning, but this side of the building has no air conditioning. So they have some, the portable or some small auxiliary AC system up there. It's not great. And look at the screen, how small it is. Can you see it? Oh, by the way, if you are sick, so you cannot attend, the exams or any important dates, that's okay. I can arrange a make-up exam or so. But that is only, when you are sick. If you have any other family member, if it is important, please discuss with me in advance, okay? You can just come later after the exam and say, this is what happened. It's not gonna work, okay? And in that way, if there's any students, that missed a lecture or something, I can record the lecture. And then, they give to the person so that he can or she can actually. We have one student missing today because of the illness, so I'm recording this lecture. I don't know how it's gonna work because there was some technical glitch in WebEx, so let's see. I know you know that this course is offered per semester, so there was EGR356 last spring, and the next, the spring. So if you think that you don't like this class, and you can register. the last semester or after this semester. No? There was EGR356 last semester, right? I was on sabbaticals. Okay, so we are going to study, the 8 chapters, and the first, a couple of chapters, like chapter 1 and chapter 2, are not fun. I apologize for that. But imagine like this, right? If you like if you like to play a video game, let's say that you buy a PlayStation, what's the latest? 2, 3, 4, 5 already? I still remember 20 years ago when I bought my first PlayStation. That's the day, the before the university entrance exam, the national university entrance exam. But I couldn't sleep on the day. I messed up my exam. Anyway, and was in place. Okay, so when you buy a PlayStation, let's say that it's a new video game. The first, the time, the first when you play, it may not be fun because you don't know how to play, right? So let's say that it is a game, the fighting between two. Then you need to know what this button A means, what this button B means, and C, D, etc. Right? So let's say that button A is a left punch, button B is a right punch, and kick, etc. Right? So consider this chapter 1 and 2 is kind of learning how to play this thermodynamics game. Okay? So once you master chapter 1 and 2, which is going to be a little bit, the boring, then chapter 3 is going to be fun, and etc. Okay? You will like this. But just to be sure that this chapter 1 is no fun at all. Okay? So be prepared. And by the way, if you have any question during the class, feel free to interrupt. Don't assume that you are the only one who have that question. Any of you may, have the same question, but kind of shy to ask. So when you think that something is not clear, let me know. Okay? Don't be shy. Yeah, don't be shy. Look how boring it is, right? So this first slide gives you the overview of thermodynamics. So if you completely understand this slide, we can say I mastered thermodynamics. Okay? How many laws in thermodynamics? The first and the second. That's all. So if you know what's going on here, then this course is going to be over today. Okay? So let's look at the first law of thermodynamics. The first law of thermodynamics is about conservation of energy principle. Do you know what it is? It's pretty simple. Let's assume that that if I eat 5 hamburgers this morning, and then in the afternoon, I poops like 2 hamburgers. How many hamburgers in my belly? How many hamburgers? 5 minus 2, 3. Then I have a problem in digestion, right? Anyway, that's a conservation of energy principle. 5 minus 3, no, 3, 2. It's going to be 3. So energy cannot be created or destroyed, only change forms. Then let's think about this electricity. Where this electricity comes from? Oh, it is created in a power plant. This electric energy cannot be created. In a power plant, we convert chemical energy into thermal energy, which means that we burn something over it to generate heat. That heat is going to make steam. So meaning is that this chemical energy is converted to thermal energy. Then this thermal energy is going to, the generate steam. That steam is going to expand under high pressure. That expansion is going to push the turbine blades inside the turbine. So then we can generate shaft work, which means that something is rotating. That will run generator, which is coupled with turbine. That generator is going to produce electricity. So that electric energy was actually, the initially chemical energy. So chemical energy becomes mechanical energy. Thermal energy, which is a heat, and this thermal energy is going to run turbine, which means mechanical energy. Then mechanical energy is going to run generator, which is electric energy. So there was no creation or destroy of energy. So that is the first law of thermodynamics. One good example is this one. There was a rock on top of this cliff. And you can see this PE and KE, what they are. PE is potential energy. And KE is kinetic energy. What is potential energy? The energy associated with gravity. So when you go up, you increase the potential energy of yourself. And if you go down, you decrease the potential energy. So, and kinetic energy is the energy associated with velocity. So higher velocity means higher kinetic energy. So when the rock was stationary on top of this cliff, you can say it has 10 units of potential energy and 0 units of kinetic energy because it has no velocity. And when it falls, then you can see potential energy is going to decrease. And in the meantime, the velocity goes up. That means that kinetic energy is going to increase. Where does this kinetic energy come from? It is from the potential energy. So if you calculate the sum of potential energy and kinetic energy, it's going to be always what? 10 units, right? Am I right? No, I'm not, because when it drops, due to the air friction, the temperature of the air, the temperature of the rock is going to increase. That means that some of the kinetic energy is going to be converted to heat. Have you seen, the documentary or something when the space shuttle is going to the Earth? Then you can see it's too hot, right? So we need to, to maintain a certain angle, not to completely burn out, right? Where the heat comes from? From the sun? No, due to the air friction. Okay? So the velocity, the kinetic energy is going to be converted to heat. And once this rock is about to hit the ground, what is going to be, but however, but the increase of thermal energy is pretty small compared to kinetic energy and potential energy. So even though we know some of the, the kinetic energy is going to be converted to heat, you can say it's not 7.3, but it's going to be 7 and maybe 2.999 or something. And a small amount of heat, thermal energy. Okay? So usually we can neglect that. So for simplicity, so let's neglect this thermal energy. Then what is the kinetic energy and potential energy when this rock is going to hit the ground? We know that the thermal energy, all the potential energy is going to be converted to kinetic energy, right? So you can say the potential energy is near 0 unit and kinetic energy is almost 10 units. So when you calculate the sum of this kinetic energy and potential energy, it's going to be still 10 units. Make sense? Then once it hits the ground, now it is at the ground, on the ground. What is the potential energy? 0 unit. And what is the kinetic energy? 10. Once it hit the ground, it still, it has a high velocity, not anymore. So the kinetic energy is going to be 0 unit. So the sum of potential energy and kinetic energy is going to be 0. Does it make sense? Considering conservation of energy principle. According to the conservation of energy principle, the sum of potential energy and kinetic energy should be always 10 units in this case. But once it hits the ground, there's no more potential energy, no more kinetic energy. Where is 10 units of energy go? It's going to be, the used, the 10 units of energy, it's going to be converted to chemical energy. Chemical energy. What kind of chemical energy? Maybe this chemical energy is associated with when the rock is breaking into 2 parts. Then the 10 units of energy has been used to break this rock or deform the ground. So eventually, the sum of these energy is going to be always 10 units because of conservation of energy principle. That is the first law. And we are going to study this first law throughout this, the thermodynamics. Okay, from chapter 1 to chapter 9. Any question about the first law? Okay, then let's talk about the second law. Really boring, right? I told you, I warned you. It's not fun. But wait until we finish chapter 2. Chapter 3 is going to be fun. Okay? That's weird. I'm really Wolverine. I feel myself. So you saw that there was bleeding, right? All right. Yeah. That is interesting. So the second law of thermodynamics, what is it? Oh, there's the answer. Heat flows in the direction of decreasing temperature. When you have a coffee like that, it's hot coffee, then where this heat goes. If I leave this coffee for, let's say, the 8 hours on this table, what's going to happen? So the heat is going to, transfer the surrounding air. So the air is going to be warm and the temperature of the coffee goes down. There's no way that, if I, place this cup and this coffee is going to absorb heat from the surrounding and it boils again. That's not possible because of this second law of thermodynamics. So when we have this coffee, 70 degrees Celsius, and the surrounding is at 20 degrees Celsius, and the temperature of this coffee is going to decrease down to, let's say, 21 degrees Celsius, and the temperature of this air is going to go up to 21 degrees Celsius. Once their temperatures are the same, let's say that coffee is at 21 degrees Celsius and the air is at 21 degrees Celsius, what is the direction of heat transfer? There's no heat transfer because there's no temperature difference. So the temperature of this coffee can go down until the temperature of the surrounding. Once they share the same temperature, there's no more heat transfer. That is called thermal equilibrium. Then, if I leave this coffee like for days, then we can expect that the temperature of this coffee is going to be at the room temperature, the temperature of this room. Okay? Any question about this first slide? So by using this first law and second law, we can explain a lot of things in terms of thermodynamics. And that's what we are going to do in this course, as well as EGR456, thermodynamics 2 and heat transfer, and EGR460, thermal lab. That means if you do well in this course, you can do well in the following two courses. If you don't do well in this course, that's not the end of the story. It's going to affect your EGR456, EGR460. So there are consequences. That's important. That's how important this course is. Dimensions and units. There are two dimensions. Yes.
The slides on Blackboard.
Yes. Slides are on Blackboard, homework assignments are on Blackboard, and also syllabus. And if I record a lecture, suppose there's any students missing due to the right reasons, then I will upload that lecture video on Blackboard too. Okay. Yes.
The sheets you're working off of are the same as the slides on Blackboard.
What do you mean?
These sheets here.
Yeah, that's exactly the same. The lecture notes on Blackboard. I downloaded it from there. By the way, this is the summary of this textbook. So don't read from page 1 to page 600. Start with the PowerPoint first. And if you have a question, you can ask me a question, or you can go to that section in the textbook. Primary dimensions are the dimensions that cannot be divided into two. Secondary dimensions means those can be expressed in terms of the primary dimensions. So for example, and in thermodynamics, there are four primary dimensions. They are mass, amp, length, time t, and temperature T. There are two T's. So lowercase t represents time, capital T represents temperature. So these are the four primary dimensions that we are going to use in thermodynamics. You cannot divide these primary dimensions. Any units that we are going to use in thermodynamics are going to be a combination of these primary dimensions. So let's see. They are called secondary dimensions. Like, for example, velocity. What is velocity? Velocity can be determined by distance over time. Distance means length and over time t. So that is velocity. In this thermodynamics, there are two different units, SI units and English units. If I, mix them, it's going to be complicated. So in this classroom, we are going to focus on SI units. And your exams are going to be also in SI units. Be consistent. However, sometimes when you go out to the field, you may have to use English units. So you also need to learn English units. So some homework assignments are in English units, so you can practice both units. However, I don't want you to practice both units in the exam because it's a limited time. So all English unit problems are going to be in your homework assignments. Plenty of time. Right? Then what is the SI unit for this mass? Gram? Now, gram is too small, so we use kilogram. What about length? Meters. What about time? Second. What about temperature? Oh, that we are going to talk about later at the end of this lecture. So this velocity is going to be in SI unit. Length is going to be meter per time second. So meter per second is the unit for velocity. What about energy? Energy has the same unit as work. So let's talk about work. Work, W. How do you determine work? Simple. It's force times distance, right? So force times distance. Distance means length. Then length is a primary dimension, right? So we cannot divide this length into two. The other hand, this force is not a primary dimension, so it is still a secondary dimension. So this force can be determined by mass times acceleration. Mass times acceleration, A times length L. Then, if you look at here, this mass is going to be a primary dimension. This length is going to be a primary dimension. However, this acceleration is not a primary dimension. So this mass is a primary dimension. That's all. We don't need to worry about that. Length is a primary dimension. We don't need to worry about that. What about this acceleration? Velocity is the change in velocity is distance over time, because we want to see how much change in distance per time. Acceleration is the change in velocity per time. So it's simple. Velocity is length over time. Then acceleration is going to be velocity over time. It means length over time over time. So two T's. So that's going to be length over time square. And we have length here, we have mass here. So energy, which is a secondary dimension, can be expressed as a combination of primary dimensions, which is mass times length squared over time squared. Okay. So this is mass times length square over time square. So what is the SI unit for this mass? Kilogram. What is the SI unit of this length? Meter square. Meter. What is the SI unit for this time? Second square. Then what is the unit? What is the SI unit for this energy? Joule. So this is joule. Okay. So this secondary dimension, joule, can be expressed as a combination of primary dimensions. Then where can we use this information about dimensions? We can apply dimensional homogeneity. What is dimensional homogeneity? All equations must be dimensionally homogeneous. What does it mean? When you have an equation, the left-hand side and the right-hand side should be at the same dimension. Okay? Then let's talk about the first example here. We discussed two different energies, potential energy and kinetic energy. Potential energy is energy. Kinetic energy is energy, right? Then do you know how to determine potential energy? You studied it, right? It's one of the prerequisites. How do we determine potential energy? Mass times gravity times what? Height, distance, right? So we can say h or z or anything, that we prefer z in this case because if you use a Cartesian coordinate system, let's assume that this is the Earth right here. It's pretty tiny Earth. And I'm standing right here. And the coordinate system on my location is going to be x, y, and z. And gravity direction is this z direction, so we prefer z. Sometimes you use h for height, right? What about kinetic energy? How do you determine kinetic energy? You remember that mass times velocity square over 2, right? Mass times velocity square over 2. Then this is energy. What is the unit of this potential energy? Joule. So the unit of this potential energy is going to be joule. The unit of kinetic energy is going to be joule. But the left-hand side is mass times gravity times elevation z. The right-hand side, mass times velocity square over 2. So how do we know this one is correct or not? You can check dimensional homogeneity. You can check dimensional homogeneity. All equations must be dimensionally homogeneous, means that the unit on the left-hand side and the units on the right-hand side should be the same. Then let's see, what's the unit on the left-hand side? Joule. And according to this, so joule is kinetic energy. Energy is work. So this energy can be work. So this work can be force times distance. Force, the SI unit of force is Newton. Distance, meter. Newton, which is a force, is a secondary dimension. Meter is It's not a secondary dimension, it's a primary dimension. Once it's primary dimension, forget about that. Then let's look at this secondary dimension. Newton, which is a force. Force is mass times acceleration. Mass kilogram times acceleration. Acceleration is meter per second square, and we have a meter. So if you look at this left-hand side, kilogram is a primary dimension, meter primary dimension, second primary dimension, meter again primary dimension. What about right-hand side? We have mass, which is kilogram. We have velocity, meter per second, and square. So if you look at the left-hand side, we have kilogram, meter square over second square. We have a kilogram, meter square over second square. So you can see this equation meets dimension homogeneity. See, that correct. So checking the dimensions of an equation is one way to verify whether the equation is okay or not. Because if you see meter per second square, but if you see kilogram here, that means there's something wrong with this equation, right? Any questions up to here? Dimensions or units? Still no fun, right? Is it too fast or too slow or good enough? Okay. If you think that I'm going too fast, just let me know. If you think that I'm too slow, then that's okay, right? I know it's the first day of this course. You must be really bored. So let's do the last slide, and that's all for today. No more slide. Systems and control volumes. So here in this slide, we are going to talk about how we analyze a thermodynamic system. So let's assume that if you want to study how the heat of this coffee is going to transfer to the surrounding air, which is a simple and straightforward. We know that the temperature of this coffee goes down, the temperature of the air goes up because of heat transfer from the coffee to the surroundings due to the second law of thermodynamics, right? So to study that, we need to know a few things. Actually, three things: system, surroundings, and boundary. In this coffee example, looks too complicated. So let me make a simple cup like this. So there's a cup, there's a coffee inside. Tasty? I don't know. What's the temperature? 70 degrees Celsius. And the surrounding is at 20 degrees Celsius. Air. What do you expect in this problem? We expect that there is a heat transfer due to the second law of thermodynamics from the coffee to the air, right? In what direction? To the right, or to the left, or to the bottom, or to the which direction? in anywhere from the highest temperature to a lower temperature. This is the beauty of thermodynamics. In this thermodynamics, we don't need X, Y, Z coordinate or cylindrical coordinate or spherical coordinate because the direction is already determined from a higher temperature point to a lower temperature point. I know that many of you don't like to hear vector, tensor, etc. Right? Here in thermodynamics, we don't worry about that because one direction from higher temperature point to a lower temperature point. So in reality, the heat transfers in every direction. However, for simplicity, in this lecture, we are going to point this way, okay? That doesn't mean that it only goes to the right. It can, the transfer in any direction from high temperature to a lower temperature. But for simplicity, I'm going to say heat transfers from this coffee to the air in this direction. And in this problem, what do you want to study? What do you want to study? Oh, I want to study this cup. What you want to study is going to be the property whose value is changing, right? So let's say that the air temperature is 20 for now. 20 minutes later, 20. And an hour later, 20. There's nothing you can study. It's still 20, right? But here in this problem, we know the coffee temperature was initially 70. 10 minutes later, 60. 20 minutes later, 50, etc. And after all, the temperature of the coffee is going to be what? 20. So the temperature of the coffee is changing. Therefore, the property that you want to study is going to be the temperature of this coffee. That this coffee is going to be a quantity of matter or a region in space chosen for study. So this coffee is what? Our system. And in thermodynamics, we know that there is a heat transfer because the heat transfer is what we want to study because the temperature is going to go down because of the heat transfer. Then, when heat transfers from A to B, due to the first law of thermodynamics, which is the conservation of heat transfer, we cannot just destroy heat. That heat needs to move to somewhere, right? So the heat of this coffee is going to move to where? To the air. So air is the one observing heat from our system. So air is also important, right? Because we cannot destroy energy. We cannot create energy when there is a heat transfer, when there is an energy transfer to or from a system. We need to study those observing or releasing energy. That is called surroundings. So in this case, the air is going to be the surroundings, the mass or region outside the system. So this air is going to be the surroundings. And what is boundary? The real or imaginary surface that separates the system from its surroundings. So what is the boundary in this example? The cup, right? But there is no just one boundary. There are two boundaries. Real boundary or imaginary boundary. Real boundary means this cup is the real boundary. What about here? The interface between the coffee and the air. That's not a cup, but that separates. This interface separates the system from its surrounding. So that's a boundary, but not real cup. That is imaginary boundary. What is the difference between real boundary and imaginary boundary? By the way, some people like to say real boundary as a closed boundary, imaginary boundary as an open boundary. Closed boundary means heat can transfer. When you hold a cup of hot coffee, you feel that it is hot. Why? How do you feel that it is hot? Because you just know? No, because of heat transfer. The coffee is transferring heat to the cup is transferring heat to your skin, and you receive heat on your skin from the cup. You can feel that it is warm. When you hold on ice, you feel that it is cold. How do you feel that it is cold? Because there is heat transfer from your skin to the ice. So, closed boundary means heat can transfer, however, mass cannot transfer. On the other hand, imaginary boundary or open boundary, heat can transfer as well as mass. So when you have a boundary, when mass can transfer, then it's an open boundary. Mass cannot transfer, but only heat can transfer. That's a closed boundary. So when you solve a thermodynamic problem, you always need to have these three: system, surroundings, and boundary. Once you determine these three, then you are ready to solve that problem. Okay? There are two different systems. And let's talk about this system. There are two different systems. One is closed system. The other is open system. What is the difference? Closed system means a fixed amount of mass, and no mass can cross this boundary, like this cup of coffee. We know there's a heat transfer from this hot coffee to the surroundings, but we know there is no coffee is transferring from inside coffee to outside, right? So it is a closed system. Even though you open the lid, it's a closed system, as long as the mass of the coffee remains inside. And what about this air conditioning system? Is a closed system or an open system? If I say it like that, it sounds like an open system, but how do you know? When you want to, evaluate a thermodynamic system, what is the number one thing that you need to do? You need to determine what is my system, what is the surrounding, what is the boundary. When we talk about air conditioning system, what is the system? When you talk about air conditioning, what is the system? The AC unit is said? Air inside the AC could be a system, or refrigerant inside the AC is going to be your system. So whatever inside flowing is going to be the system. So the AC, the air handler is going to observe air and trying to remove heat from there and release it. That's how, it cool the air inside, right? So there's air goes into this air conditioner and then air is emitted by the air conditioner, right? So air is flowing and the AC is going to be an open system. Yes,
If you made the refrigerant your system, would it be a closed system?
what do you mean?
You said you could make the refrigerant inside the AC your system.
Refrigerant is a working fluid that is going to transfer heat from inside to the outside.
Right, but
So that is flowing between the air handler here and the outside unit of this building, the usually on top of the ceiling.
Yeah.
If you have AC, the central air system in your house, in the backyard or side of a house, you see there's something, the noisy machine, right?
Yeah.
That is a compressor. So what this AC does is that their refrigerant is, the moving between outside the unit and inside unit. So we observe heat from inside and release heat to the outside. So if you consider this AC unit, the compressor, outside, external unit, inside unit as a single device, then it's a closed system. But if you consider this external unit alone, then it's an open system because the refrigerant is going in and going out. If you consider air handler as your boundary, then it's an open system. But if you consider both of them as the big boundary, then it's a closed system. So it depends on how you define your system. Any question? Okay, so I know that it is too much for the first day, so let's stop here. But we still have 10 minutes. So what do you want to do? Continue to the next slide. Yes.
Just out of curiosity, if you considered like the edge of the universe, your boundaries, would you have a closed system, or is there some limit to that?
Whole thing is that there's no matter. It's to be net zero.
When you want to define a system, you also need a surrounding where the energy is transferred to.
Okay.
So it say that you have this big universe, and if you just define this big universe as your system, where is the surrounding? There's no surrounding, right? So if you only consider half of the universe as your system, the other half as a surrounding, then this thermodynamics works because there is an energy transfer. But if you consider the whole system without surrounding, then you cannot define a thermodynamic system.
Okay.
Okay, and is that it? No. Okay. Let's talk about some of my work. What I do. You don't want to hear that? It could be interesting, okay? So if you go to my website and click this, my research website, it goes to here. So what I do is, that I study part of thermodynamics. Be fun. Okay? So this is the solar power plant. Looks different from, what you expect when you hear solar. So usually when you hear about solar energy, you imagine like, the black panel that you install on top of your roof or something, right? So there are two different ways to harvest solar panels. One is through the black panel, which is a photovoltaic system. It is a combination of series of semiconductors directly convert the sunlight into electricity, which is pretty fancy and straightforward. On the other hand, this one is called concentrated solar power, which that use a number of meters trying to reflect the sunlight into a focal point, which is the black dot on top of this tower. So we can generate high temperature heat, usually over 1,000 degrees Celsius. Then we can use that heat to run conventional, the thermodynamic cycle, the way we produce electricity in general. Right? When we talk about power plant systems, unless renewable, we have a nuclear power plant, hydraulic power plant, and fossil fuel power plant, geothermal power plant. In most of these power plants, what we do is that we generate heat somehow, maybe nuclear reaction in a reactor, or the burning fossil fuel, or core natural gas, or the pumping geothermal, the water steam from underground, or concentrate the sunlight, and we use that heat to generate electricity. Then what is the difference between the photovoltaic system and this system? Each one has pros and cons, but in a photovoltaic system, it's simple. You can buy this small photovoltaic system, solar panel, install on top of roof. You can produce electricity right away when the sun is up there, and then you use it. And when the sun is gone, you cannot produce electricity anymore. So you can run your refrigerator in the daytime. You cannot run your refrigerator in the nighttime, right? Unless you have, the millions of Tesla, right, to charge the electricity. So that the good thing about, the photovoltaic system is a simple, and that it can be small scale, but the cons is that you cannot produce electricity 24/7. In this system, the fun thing is that we produce high temperature heat by reflecting the sunlight into a focal point. Storing electricity is pretty hard, but storing heat is very simple. You see this, the giant tanks. You can fill this tank with water or fill this tank with liquid salt, and depending on the temperature that you want to use, you want to run turbine systems. So you concentrate sunlight and then heat something of a mass, and then use that heat to run the turbine, regardless of the sun is up there. So you can produce electricity 24/7. Then, why do we know about photovoltaics? Why we don't know about this technology? You never heard about that, right? Because you need to generate high temperature heat. You cannot install this one in your backyard. That's the problem. So usually we are not the customers. Customers are country government, or the federal government, state government. So they don't do advertisements to ourselves. It's a B2B business, not B2C. So many of you heard about the photovoltaic systems. You didn't hear about this concentrated solar power system, but we have more than 50 concentrated solar power plants in US. Interesting. What I do is that I develop thermal energy storage materials, trying to increase the life of this energy storage system so we can produce electricity for 24/7. So that's what we do. And these are, what we do. And some accomplishment that we did is that, we are, the selected top 2% of the scientists in the world. There are only 9 people in CMU was selected here. And there are number 9 in solar thermal energy in the world. One of the, the accomplishment we did in our lab, just for your information. And these are the publications. So these are things that that we do in in terms of research in our campus. Of course, if you go outside, maybe the MSU and U of M, or the MIT, or the Harvard, they all have very state-of-the-art the laboratories. As an engineer, as a student studying engineering. You may want to, get to, to start learning about, what we do, when we talk about, the advanced, the engineering. Okay? So just to give you an overview about, what I do briefly, and then you can, taste, what, the engineering can do in the future. Does it make sense? I just thought that, talking about chapter 1 for 1 hour, 15 minutes is going to be too much. So I shared, the 15 minutes to talk about, some of the work that, that we did at graduate school. Okay? Any question? No? Okay, then that's all for today. And, the see you on Thursday. By the way, my office hours, right after this class, if you want to see me, you can come to my office, E234, or if you don't want to see me, but still want to talk to me, you can use WebEx on Blackboard. I usually turn that on by, the WebEx meeting in the application.